All right. So our learning target for today, again, this is a section that's sort of heavy in vocab. So our learning target for today is that we're going to be able to determine if a function is linear or non-linear. I'm going to show you guys how to do that algebraically, but there's a lot of key things you guys can look for that's not algebraic to prove this. We're also going to find x and y intercepts. So, some definitions for us. Let me make sure I'm not muted somewhere. Okay. So some of this is review because it's from Algebra 1. So our first term here is in a linear function. In a linear function, no variable is raised to a power other than 1. In fact, you guys normally don't even see a power there. It would just be like an x, because it'd be an x to the first power. Yeah. You can't see it. Do you need to sit closer? There's an empty seat up here. Any linear function can be written in the form y equals mx plus b. This should look really familiar to you, where m and b are real numbers. This next part, I'm going to write it because it's in our book, but we're not going to use this ever. This is sort of a subtle difference that I don't think we really need to focus on, but linear functions can be represented by linear equations. Linear equations, it's right here. I think, or where do you put it? This one. They can be written as linear equations in the form ax plus by equals c. If you ever interacted me with it, like in Algebra 1, that's called standard form. I think it's a pointless form for linear equations. I don't really care about this little part. But basically, the key part here is that a linear equation is a straight line. So anything that's not linear is called a non-linear function. And there are lots of them. A non-linear function. So one of the most important ones for Algebra 2, Algebra 1 is always it's just like about linear functions. You do other stuff as well, but really it focuses on linear functions. And Algebra 2 spends a great deal of time talking about a quadratic function. So a parabola is the graph of a quadratic function, which is a type of nonlinear function. And it's the function we really like. It's this second one here. Bless you. It's an x to the second. We'll do a lot of things with that. But you guys can see all the different kinds of functions that exist in the world. I believe the ones we'll be focusing on are in these top 2 rows, and really the top row in particular. We will not get to sine, cosine, or tangent. Let's say that's a 2b concept. So hopefully you guys can recognize a linear function from the graph. But what happens when it's not in a graph form? So there's really 2 ways you can do this. The first way is that you can determine if it's linear by solving for y and trying to rearrange it to be y equals mx plus b. So solve for y. Because if you can solve it for y, if you can make it look like a y equals mx plus b, it is linear. So this first one, the first thing you might want to do, and hopefully you guys are familiar, but that f of x, that's called function notation. We use it a lot. It is actually very handy. But if you're not used to it, it really is the same thing as y. It's just saying it's a function with respect to x, meaning the function's name is f with respect to where your variable is an x instead of a y or an a. If I want to make this look like an mx plus b, hopefully you guys know this rule about fractions, but if not, when you have 2 things in the numerator and 1 thing in the denominator, you can split this into two separate fractions with that 3 in the denominator of both. That's sort of like undoing getting a common denominator when we add or subtract fractions. And then what's 6 divided by 3? 2. So is this linear or not? Does this look like a y equals mx plus b? And if you weren't sure, at this point you could type it in a calculator and see that it's a straight line. So this is linear. All right, I'll be a little briefer with part B. Do we think this is linear or nonlinear?
Non-linear.
Okay, I heard alinear, but then it sounded like it got switched to nonlinear. Why do we think nonlinear?
The theory.
Yeah, there's an exponent that's not a 1. This right here means this has to be nonlinear. In fact, on that picture in the front page, this would be our cubic function, the little guy that dances like this. Okay, the cubic. So this is not linear or nonlinear because of that third power. So basically the things you guys want to look for, if you see a root, if you see a power that's a 2 or a 3 or a 4 or anything above that, if you see an x on the bottom of a fraction, those are all things that show that it's not linear. So maybe we'll make a little list here. To the side, if you want to make a list, non-linear, make an unofficial list. If you see a root, if you see an x, do you guys mind if I put to the n, like n, x to any power other than 1, is that okay? We do a divided by x, where x is on the bottom of a fraction. Those are all bad things. Well, they're not bad things. They're just different kinds of functions. So how do we feel about identifying a linear versus a nonlinear function from just an equation? Can we do this? Okay. Then let's look at example 2. This should be even quicker. This is from a graph. Part A. Do you think this is linear or nonlinear?
Nonlinear.
Nonlinear. And if you were to look at that, the graphs on the first page, does anyone know what kind of graph would this be? Yeah, this is an absolute value graph, which we'll play with a little bit in this class. They look like a V. It's where you take the absolute value of a number so you can't have negatives. Although this does because it got shifted. What about part B? Linear, because it's a line. Straight line. Questions about example 2? And hopefully this is an indicator that you probably don't need to show your work on today's homework because not a ton to show. Example 3. Okay. So I like to throw in these story problems because I do want to prepare you for the SAT or whatever state test you have to take, and they love these. So this is identifying linear function from a table. There's a couple ways you could do this. You could do this where, do you guys remember the formula for slope? Anybody? y2 minus y1 over x2 minus x1, you remember that? And so you could basically find the slope between these two, these two, these two, and those two, and make sure they're the same. I think that's a lot of work. So let's not do that. Instead, that's how we could do it algebraically, but instead, let's plot points and see if it makes a straight line. The other thing to think about is the context of this problem. So this is an earnings problem. It says Michaela has started working part-time at the local hardware store. Her time at work steadily increases for the first 5 weeks. The table shows her total earnings each of those weeks. So we want to determine, are her weekly earnings modeled by a linear or nonlinear function? So before we start this, let's think about this. Who in here has a job? Okay. Is your job, let's pretend overtime's not a thing. Do you make the same hourly wage if you work 1 hour versus if you work 2 hours? You make the same hourly wage, right? You make more money, but your wage shouldn't increase. Like if I worked an hour at $10 an hour, but then for 2 hours, it was like 12 hours or $12 an hour, that'd be weird, right? So we should expect that this is going to be linear, but let's prove it by plotting some points here. So we have to kind of guess here. This is counting by 40s. So for 1 week, we're at 85. It's right about there. Not going to be perfect. At 2 weeks, we're at 119. So that's just below the 120. At 3 weeks, we're at 153. That's like here-ish. At 4 weeks, we're at 187. So that's like here-ish. And at 5 weeks, we're at 221. Right about there. They look like a pretty straight line. So as expected, this is probably linear. So we're going to say it's linear, preponderance of evidence. Again, you could do this algebraically with the slope, but who wants to do that? I don't. Do we have questions about linearity versus nonlinearity? Okay, so the last thing I want to talk about is intercepts. These, I find students tend to get these just fine. The only thing is I have a lot of students that switch that x and y, right? Because we forget the order for our ordered pairs. So some definitions for us. A point at which the graph of a function intersects an axis is called an intercept. So you have two kinds of intercepts, an x-intercept is the x-coordinate of a point where the graph crosses the x-axis. So notice on the bottom here, the x-intercept is always a number, comma, 0. A number, comma, 0. Versus your y-intercept, which is where your graph crosses the y-axis, and that's always going to be 0, comma, a number. So again, linear functions tend to be easier than nonlinear functions. Remember on Thursday last week we talked about linear functions, their domain and range is all real numbers for both. And it turns out for intercepts, they're kind of nice too, because they only ever have one x-intercept and one y-intercept. So you won't have a crazy list here. If you look at part A, I actually have one intercept only anyways. It just happens that the x and y-intercept are the same for part A. So I will color code. My x-intercept. What is my x-intercept at? 0, 0. Okay, my y-intercept is also there. So I do have to list it twice, but my y-intercept, 0, 0. So on formative, you'll have to do a parenthesis, number, comma, number, close your parenthesis. That one's a little boring. Let's look at part B. Here I have a distinct x-coordinate and a distinct y-coordinate. So my x-coordinate, my x-intercept, should be a little more precise. All right, what is that x-intercept? First of all, is it positive or negative? Negative. Negative. And then, yeah, 1, 2, 3, 4, 5. What's my y part? No, what's my y part of my x-intercept? 0. 0. And then, yes, I heard the y-intercept. But what order do I put it in?
0 first.
0 first, then the 2. And again, I think we all know that, but sometimes when you really get rolling with these problems, that's probably the #1 mistake, is that we just flip those two. Okay, I'm going to do one more example, and then I will turn you guys loose. All right, I'm going to do example 5A. Real quick, let's notice some things here. So example 5 is all nonlinear functions. What do we see about the x-intercepts for this? There's multiple. There's more than one. In fact, this one has 3. I'm going to skip B because B has 1, 2, 3, 4, 5 x-intercepts. What do you guys notice about the y-intercepts? How many are there? There's 1. This is true of all functions. This is that 1-to-1 thing where it passes the vertical line test. You'll only ever have 1 y-intercept unless I give you something that's not a function, which I don't think I'll do, but I guess I won't make any promises. So let's look at our x-intercepts to start. I'll highlight them, and then we can start listing. So x-intercept, I'm just going to go from left to right. I have -3, 0. I have -1, 0. And I have 2, 0. Oops. For my y-intercept, what is my y-intercept there?
12.
Nice. How do you know it's 12? I thought it was 3.
Because it says 8 and 16, and in between 8, the direct middle of 8 and 16 is 12.
Yeah, so just pay attention, be mindful of what your axes are counting by. Just as a note, if you do look at part B, it doesn't show what it's counting by. If it doesn't show what it's counting by, you assume it's counting by 1, okay? Because otherwise, I don't know, that'd be a mean math teacher. Okay. Find my mouse.